Alright, jumping into lesson 1.3, we're going to start taking a look at some parent functions. There's 12 main parent functions that our book wants us to know about, so we're going to just sketch those out real quick. Most of these you're already going to know. Just a couple of these that maybe you haven't run into in the past. Just start out with the most basic, y equals x. So we know that would just be our linear function that goes right through the origin with a slope of 1 over 1. Some extra details if you want to find more information about any of these guys. Take a look at page 96, 97, and 98. It has all these guys laid out with some a little more information on these, but we're going to kind of run through the basics here. So as far as our parent function for a quadratic, we know it's just our parabola that goes through 0, 0. Our cubic function is the one that looks like our S shape that runs through 0, 0. There's our cubic function, parent function. For our square root function, remember that one you can only take the square root of a positive or 0. So that's the one that starts at the origin and does this. Our reciprocal function or rational function for 1 over x. This guy has vertical asymptote through 0 and a horizontal asymptote through 0. So we get the curves in quadrant 1 and quadrant 3. So that's our reciprocal function. E to the x, so our exponential growth functions. These are the ones that have a horizontal asymptote through 0, but the main point we always kind of recognize with these guys is it runs through the point 0, 1. So let's treat this guy as 0, 1, and we're going to get our exponential growth would look something like this. Natural log of x, so remember the relationship of natural logs and that e function, and that's something we'll be looking at a little more on later on. We do a chapter on logs, so we'll get into that stuff a little bit later, but our basic natural log function is sort of an inverse of e to the x. So where e to the x has a horizontal asymptote through 0, logs have a vertical asymptote through 0. And so instead of going through 0, 1, natural logs go through 1, 0. And so we get the inverse function of e to the x doing something like this. So that's our natural log of x. Your trig functions like sine and cosine, we're going to be working with those guys a little bit later on as well. So your sine function and your cosine function are really closely related. Your sine function starts at the origin, and it will go up 1, goes back down to 0, goes down 1, and back up to 0. And that's just one full period. This can keep going on forever and ever and ever in both directions. So keep going on and on and on. So I'm just showing you one full period on the sine function that goes from 0 to 2 pi. The cosine function is really the same thing. If you were to take this guy and sort of shift it left pi over 2, you would get the cosine function. Cosine function starts at 0, 1, goes back down to the axis, goes as low as -1, back up to 0, and finishes at +1. So, and again, that's just one full period. We could continue on and on with those guys. Those curves go on left and right forever. Absolute value of x. This guy, absolute value, can always remember that v of value. That's the shape of your absolute value function. One thing I wanted to show you on this, because we're going to be getting into this later, if you think of just the graph y equals x, remember that y equals x was this graph right here, right? That would be the graph for y equals x. But as soon as you put the absolute value on it, you know the absolute values make everything positive. So it takes the negative portion of the graph and it flips it up into the positive. So it looks like this. So that's why we get a V shape when you throw in the absolute value, because it takes the negatives and it turns them into positives. So now they're above the x-axis instead of below the x-axis. So we get the V shape for that one. These are the two that I think would probably be totally new to you. The greatest integer function, also known as a step function, has to do with finding the greatest integer within a group of numbers. So if I had a number like 1.5, what would be the greatest integer up to that point, right? The greatest integer up to 1.5 would just be 1, right? Remember, integers are not decimals. They're like the whole numbers that you would land on. So the greatest integer function has to do with identifying the greatest integer up to a certain value. So here's kind of the way this one looks. And we're going to call this 1, 2, and 3. So the greatest integer function all the way up to 1 would be 0. Because if I had a number like 0.5, well, what's the greatest integer up to this point? Right? It would be 0. One of the rules you always get with greatest integer functions is like you always round down, right, to the greatest integer. Because even if I had 0.9, like, and if I said what's the greatest integer up to that point, well, it's still 0. That's still the greatest integer up to this point. You don't get to have this as your next greatest integer until you land on 1. So it's like it's all the way up to this point, but as soon as you land on 1, now you're up to here. Because if I were to plug in 1 into that function and I said what is the greatest integer up to 1, right, it would be 1. And that's going to stay 1 all the way until you get to 2, but does not include 2, because as soon as you land on 2, now the greatest integer is 2. And that would stay the greatest integer all the way up to until you get to 3, and so on and so on. And it's going to go down into the negatives as well. Call it -1, -2, just to give you a couple more. So again, the greatest integer from -1 to 0 would be -1, because this is our -1. So as soon as you get to 0, now you jump up and the next greatest integer is 0. So these guys just kind of go on like this forever. And so that's what our greatest integer function looks like, or our step function. We're not going to be working with the logistic function too much. Kind of the main thing that you hear about the logistic function is it has 2 horizontal asymptotes, one at 1 and the other at 0. The logistic function is more of a business model type function. We're not doing a whole lot like with this one, like I said, but at least let me introduce it to you. So it looks a whole lot like this. And that's what we call our logistic function. So just a quick mention about symmetry and continuity, because we've already talked a little about both of these so far, so let me just mention them. For the most part, most of these graphs are continuous from -infinity to +infinity, right? Certain graphs like this are discontinuous because of the break in the graph. So we talked earlier on about the 3 different types of discontinuity in our earlier lesson, but we can see there's discontinuity here. When you get to, obviously, that greatest integer function, right, there's clearly a jump discontinuity, right, as we jump from 1 to the next part of that graph. So we have the jump discontinuity with those, but most of the graphs that we see sort of go on and on forever, left and right. And so they are continuous everywhere. But a couple of these guys are discontinuous graphs. As far as the symmetry, like we've already talked about, remember if it is symmetric to the y-axis, like this guy would be, or like our sine and our cosine graph would be, right? Because I can fold this across the y-axis and get a mirror image on top of itself. So symmetric to the y-axis makes it an even function. If it is symmetric to the origin, like if I could flip my paper upside down and I'm still looking at the same graph, I know it's an odd function. So if you look at, let's say, these two graphs, I can rotate this page 180 degrees and I'd still be looking at this exact same graph, right? So we know these are odd functions. So just don't lose sight of some of those ideas that we've already talked about, but those are the main graphs that we're going to be working with. So let me jump to a couple examples. You learned in Algebra 2, you learned about doing some transformation rules like shifting left or right, doing some reflections, things like that. So I'm going to remind you of a few of those rules here. So if you look at the graph of x minus 3 squared, right, remember what we would have on that. Here's what it looks like, but we know where that comes from. If I took the parent function of y equals x squared, which we just drew on the other page, so I know the parent function looks like this, and anything inside those parentheses, remember anything that's attached to x is going to affect your graph left and right. When it comes to the pluses and the minuses in your horizontal shifting, they always do the opposite of what you would see. So when we see a minus 3, we're actually going to the right 3 units. And so that's where this graph comes from. So as far as what interval is it increasing or decreasing, so right here where it's heading downward is my decreasing. And then from here to here is my increasing interval. So we would say as far as like decreasing, we would say that it is decreasing from negative infinity all the way up until I get to 3. Because remember, this goes on and on forever, right? So from negative infinity all the way until I get to 3, it was a decreasing function. But from 3 to positive infinity is going to be our increasing function. And so those are the ways we would have written that. As far as odd, even, or neither, we can see on this one, graphically we can tell that it's just neither because it's not symmetric to the y-axis or the origin. So we can tell it's neither. If you weren't looking at the graph, remember you can replace x with negative x and see what happens, right? If all your signs change for the whole thing, we know it's odd. If nothing changes, we know it's even. And that just wouldn't be the case with this guy here. So as far as relative extrema, that's just referring to a maximum or a minimum. So you can see right here that this does have a minimum point, what we would call the vertex. We have a minimum point at 3, 0. And so that would be something we would call an extrema. How does it relate to this graph? We already talked about that horizontal shift because of the minus 3. All right, so there's just a couple basics on what we're going to be doing with these. Let me move on. So let's practice a couple of these. And we're starting out with just some pretty familiar functions here. These are both parabolas, right? They're both x squared functions. Just wanted to remind you of your few of your rules. And so think of the parent function. So we just showed how this would shift my graph to the right 3. And what would that negative do? So when you put a negative out in front, now you're going to do a reflection up and down across the x-axis. So we're going to go right 3. 1, 2, 3. But it is now being reflected downward because of that leading negative. So we're going to get something like this for this graph. Really helps to sketch a graph and to know those transformation rules, because now answering those other questions are really simple. So where is it increasing? I can see that it is increasing from negative infinity all the way up to 3. And that would be inclusive because there is a point on the graph at 3, 0. So we would say from negative infinity all the way up to 3, inclusive is increasing. And then from 3 to positive infinity, also inclusive, would be our decreasing portion of that. And just a reminder on something we said earlier video, increasing just means that as I move from left to right, the y values are getting bigger, right? And that's all that it takes to be an increasing portion of the graph. And decreasing, the y values are getting smaller as I move from left to right. So we know those are decreasing. Notice on this one, now the -1 is not inside of parentheses. So now we're looking at a vertical shift. So we're going to take our x squared function and shift it down 1. So we'll call this -1 right there. So our vertex is now 0, -1. And we're going to get that graph right there. And so again, to answer those same couple types of questions, you can see that the decreasing interval is from -infinity to 0. And then the increasing interval would be from 0 to positive infinity. Odd, even, or neither. This one, by the way, was neither. However, this one over here is an even function. So you can see by the graph that it reflects over the y-axis. Also, if I replace this x with -x, I'm still going to get x squared minus 1. So let me jump on down to a piecewise function. A piecewise function, or otherwise known as a hybrid function, is basically putting a couple graphs together on the same grid, but we restrict their domain that you graph them within. So instead of going on forever, you're only looking at maybe portions of the graph. So if you look at this portion of this graph, you can see that it's just our basic parabola. It says the vertex is at 0, 0, so I know it's just y equals x squared. And I wish they would put arrows on these. I'm going to put arrows on it. So that's what it looks like. So you can see that this is the general graph of the parent function of a parabola, but once you hit x equals 2, right here, it now turns into something else. So if you see right down here, this was the x squared graph, but only where x was less than or equal to 2. In other words, it's x squared in this window right here, but as soon as you hit x equals 2, right, now it turned into a different graph. And so as I look at this graph separately, this linear function is just a horizontal line at 4. So we would just call this, the equation of this graph, y equals 4. But it's not y equals 4 forever. It's only y equals 4 from positive 2 up to infinity. And so we're defining the domain of that portion of the graph as the x is greater than or equal to 2. Right? So it's like right here at positive 2 is it transitions into a different type of a graph at that point right there. Notice that it is continuous. Right? There are no holes in the graph. There are no breaks in the graph, no asymptotes, vertical asymptotes that would break up the graph or anything like that. So it is continuous from negative to positive infinity. But yeah, so that's what those guys look like. So we're going to practice a couple here. And so I just sort of highlighted a couple just to try to give you some variation of what we're seeing here. So see if we can identify the description of these functions that we're seeing on this. So we're going to start with number 8 here. So this one you can see starts out looking like our absolute value graph, that V shape right here. So it has this line that I'm seeing, but as soon as it hits 0, 0, now it's turning into that curve that I see right there. So let's see if we can separate out what those two graphs are. So I do have the absolute value function. So we're going to say f of x equals, and this is where we can break it off into two different types of graphs. So I do have the absolute value function, but we have to identify the domain on which we're seeing the absolute value function. It only goes from negative infinity up to 0, inclusive, right? And so for the domain on that, we're just going to say it's only for the x's less than or equal to 0, right, would be the domain on that. Then we transition into this guy, and what does that look like as far as the parent functions that we just discussed on the other page to start this lesson. It starts at 0, 0 and just starts taking this arcing formation that we see on that. And so we're seeing this as that square root function that we looked at a little earlier. So we know this is the square root of x. And it's only for x is greater than or equal to 0, which, by the way, is the domain of the square root of x anyway. So because we don't have negatives for a square root function. So that was what we're seeing on that. And you could always test a couple numbers. Like if I said, what's the square root of 4? We know it's 2. Well, here you go. At the point 4, 2, we're still on the curve. Right? So I know I'm on the right track with that square root function right there. Let's take a look at number 11. So for this one, we have our linear function right here, y equals x. So we're going to say our function of x, and then here's where we'll split into our two functions. So I just have basically x, right? You can see it goes up 1 over 1, and it runs right through the origin. So it's just y equals x, but it stops at 0, 0. So it's only for x's less than or equal to 0. As I look at this one, what does that look like to you? Right, it's just the right side of a parabola. So it is our x squared function, but we are only seeing from 0 to positive infinity, so it's only for x's that are greater than or equal to 0. All right, so that's how we would identify that one. Here's that greatest integer function that we talked about earlier. Let me just set this up here. So on this guy, we have our greatest integer function all the way up to 0. So we have our greatest integer function, so we're going to just write that as an integer of x. Since it's to all the way up to 0, we're going to say for x's. So on this one, this is actually one where I sort of disagree with the book's answer on this. So they had it written as x is less than or equal to 0. That's not the way I'm seeing it, because there's an open circle right there. If we were including 0, we would have a filled in point at 0, 0. So this is the way I would have written it. The book's answer said less than or equal to 0, but like I said, I don't fully agree with that one. So we're going to agree to disagree at this point, and let me take a look at the second part of this graph. So there's actually two correct answers you could use for this one. We could just see it as our linear function of y equals x, and that would work. So we could just put an x for that. If you were to say it represents the absolute value of x, that would work as well. That would also fit that part of the graph. And so you could actually write it either way. It's two correct answers. And again, I would have said on this one for x is greater than 0, because that point is not inclusive with that open circle. Again, the book's answer wrote it as greater than or equal to 0, but I felt like that was maybe an error. So let's move on here. So what if we were going to graph one of our own? So if I was going to graph our rational function for x is less than 1, I'm actually going to do this with a pencil so I can erase a portion of this. So remember, for 1 over x, you basically get a graph that looks like this. I'm going to do this super light. Hopefully you can see it, but I just want to sort of show you something. So what this is saying is, so here's the entire graph, but we're only going to do it for x's less than 1, which means this is all I get to keep, would be this portion of the graph, from what you see from here to the left. So I'm going to get rid of everything to the right of 1 and only keep what is less than 1. And because it says less than 1, that also means I need an open circle where x equals 1, because there's no equal sign on that. And then this portion of the graph is also less than 1, so we get to keep that one as well. So, and then to the right of that, we're now looking at the square root of x. So again, remember the square root of x starts at 0, 0 and does something like this, right? It's the arc that does something like this. But we're only going to keep that portion of the graph that is greater than or equal to 1. And so at 1, 1 is where that graph would begin, right? Because the square root of 1 is 1. And so now this point is now occupied by this graph as it heads off in an arc to the right. And would do something like that. So one thing to note is if a point is occupied by either graph, then it is occupied. And so that's something we should have filled in. Anyway, let me move on to the last page. And I just wanted to mention something on this. No real work to do right now, but when it comes to looking at any of these graphs, there's just a lot of things they can ask you about. And so just wanted to kind of give you a quick list of things that you should always be able to recognize for any function. We've already talked about domain and range, whether it's continuous or discontinuous, the intervals where it's increasing or decreasing. We've talked about symmetry and odd or even functions, maximums and minimums when it comes to those points, asymptotes, end behavior, all that type of stuff. So we've now talked about all of those things. And so those are just things that you need to be aware of when it comes to any of these. So in some of these, they're just saying, let's just analyze a graph. And so if you take a look at any of those functions, we can analyze it with so many different pieces of information. So I just wanted to at least mention this to you so you could see kind of a quick sort of rundown of all the information that you're going to see right here. So one of the things that we didn't really talk about was when a graph is bounded. So bounded is sort of where you would kind of like where you would see an asymptote. Like on this one, you can see this one only goes up forever. So they say it's bounded below, like in other words, like there's a boundary here that it cannot cross. So this one is bounded below because it only goes up forever. So if it were to go, let's just say up and down, then it would be unbounded, right, in a case like that. So anyway, that is it for 1.3.